Today we are going to look at a framework called R3Corda. So our agenda for today is revision of blockchain concepts, Corda roadmap, overview of distributed ledger, Corda features, Corda network overview, and Corda concepts. So let us just revise our concepts of blockchain. So as you can see on the screen, the blockchain is nothing but a sequence of blocks which consist of certain transactions. Okay. Now, if we want to look at it from a different angle, we can say that it's a decentralized, trusted public ledger that is available for all transactions. What are the characteristics of blockchain? First, it is decentralized, that is, nodes on the network manage and maintain the blockchain, and they may be segregated across the globe. Trusted, they are distributed and verified using a mathematical formula. They are immutable, that is, they are unchanging over a time. So basically, once some approval has come or agreement has come, they do not change. They are public because everyone and anybody across the globe can see the transactions. They are pseudonymous. Basically, you can say that they are anonymous for the users. A user is able to see them but might not be able to understand them. And they are programmable. So you can write smart contracts using different programming languages. Okay, so we saw what is blockchain. One of the properties of blockchain was that it is public and can be seen by anyone. So this slide gives you the glimpse of how it can be seen by anyone. The screenshot visible here is taken from a website called blockchain.com, and as you can see, it shows you the list of blocks. It has some column headings like height, hash, mind, miner, size. This record is of a particular block. The height basically means number of blocks in the chain, hash is the unique ID, miner means who has mined this block, and size is the size of the block. If you want to go into details of these blocks, you can click on one of these fields and you'll be able to get a new page where you'll be able to see the details. This screen has been captured a few days back, so if you look at it right now, it will not be exactly similar to what you are able to see over here. As of now, we are not going into details of it. It was just a demonstration that it can be seen by all. Okay, so next is type of blockchains. Blockchains can be categorized as public and private. Few public blockchains which are very popular are Bitcoin, Ethereum, and there is a plethora of them which we are not listing over here. Private and permission basically are controlled by certain entities, net or regulatories, and they are used majority of the times in financial transactions, but not limited to them. So a few examples of them are Hyperledger, R3Corda, Ripple, Quorum, and many more again. Okay, so now we are going to look into some important concepts of blockchain. I have listed three here. They are not limited to these three. There are many other, but these three are very important. The first one is hash, second one is nonce, and third one is Merkle tree. So let us have a look at what is hash. Hash basically is a mathematical function which converts a huge set of data into few character sets. So possibly you may have something like SHA which will convert your entire data set into a 64-bit character and so on. Nonce is something which is used by miners to validate the block, and Merkle tree again is a validation factor. So let us have a look at the figure, the first figure which says list of data blocks in blockchain. Observe that in this chain we have a block which is named as Genesis block. Genesis block is the first block of the blockchain. Once the Genesis block has been created, later on the new blocks can be added into it. So you have now second block, third block, fourth block, and so on till you have the last block. If you observe the second block, you will be able to see the exploded version of the block wherein you have two components of a block, one which is called as header, that is a block header, and second which is called as body or body of the block, which basically contains the transaction. The header part has previous block hash, a timestamp, a version, a Merkle root hash, a nonce, and a difficulty target. We are not going to go into details of them as of now. The body has all the transactions that have been listed. But if you observe, there will be three aspects, that is nonce, Merkle root hash, and previous block hash, which become very important aspect in identifying whether there has been a manipulation in the block or not. Previous block hash, nonce, and Merkle root, I am repeating, are the three factors which decide whether the block has been tampered with or not. The Merkle root is something which is, again, as already mentioned, being used in the validation of the block. If you can observe figure 2, you are able to see how the Merkle root is created. If you are having 4 transactions as of now, starting from T0 to T3, as you can see in the figure, namely TX0, TX1, TX2 and TX3, what you generate is individual hashes of these blocks. So you have hash 0 for transaction 0, hash 1 for transaction 1, hash 2 for transaction 2, and hash 3 for transaction 3. You further ahead go and generate a hash by combining hash 0 and hash 1, which becomes hash 0 and 1, and similarly hash 2 and 3, and which further is again combined and converted into a root hash. This has happened because we had even set of transactions. If there was an odd set of transactions, then we have to virtually add a transaction into this particular aspect. So this is how the Merkle root is actually generated or created. Okay, so let's have a look at the industries that might be affected using blockchain. We'll start with smart contracts. In smart contracts, you may have digital rights, gambling, escrow as the entities which will be using blockchain. It may be used in digital currency and fraud reduction. It can be used in e-commerce, global payment, remittance, P2P lending, microfinances. In record keeping, it can be used for loyalty programs, supply chain, ownership, proof of identity, or intellectual property. And in securities, it can be used in derivatives, crowdfunding, debt management, private markets, or equity. These are not the only things that it is affecting. It might affect anything that a programmer might come up with, or any new industry that might be interested in using it. The scope is wide open. Having seen where blockchain can be used, now let us have a roadmap of how blockchain came to be known or has become DLT, that is distributed ledger technology. As we all know that Bitcoin was launched in 2009, and its popularity grew so much that between 2009 to 2015 a huge number of Bitcoins came into market. Some of them were Litecoin, Namecoin, Peercoin, Gridcoin, Dash, and many more. Around 2015 Ethereum was available in the market, and along with that there were other coins which were called colored coins or meta coins, which were modifications of the initial Bitcoin. In 2016, or rather say 2015 end, R3, a company which was into blockchain technology, formed a consortium with around 300 companies. And in 2016, early 2016 rather, April 2016, Corda was formed and was converted for an open source entity in November 2016. Today and around 2020, we have fourth version of Corda, and a lot of activity on Corda is happening in financial sector. Before we look into R3Corda in detail, let us have a look into a shared ledger vision. Now, we all know that for a transaction to happen, there have to be two parties, and the figure shown in the screen gives you three different views of how the parties would be doing their transactions. So as you can see, the first figure, which is bilateral and reconciliation model, here two parties are involved into sharing of some data, but in this case they are having a duplication of the data at both the places, and they are having their share of discrepancies also. They do share the data, but the business logic and the actions are taken with respective entities. Here the entities have been named as Bank A and Bank B. Okay, in figure 2, as you can see, the third party or the market infrastructure. Here also bank A and bank B wants to do some interaction, but here we have added one another entity which is known as a service provider. This service provider now has been given the capacity to share the data that is required, or to store the data rather, that is required for actions or requirements of bank A and bank B. Some of the important decisions will be taken by the service provider, and it also has a delegation of control and certain responsibilities. Okay, now the new version that has come into market today, which is called shared ledger version, wherein all three are now considered to be responsible. So bank A, service provider, as well as bank B, what they do is, rather than having a single control of data, have a shared ledger platform wherein the data based on the permission basis will be available to each of them, and they have a shared perception rather than having individual perceptions, as can be seen in the previous two figures of bilateral reconciliation and third party. So everybody has a similar perception of what the data is supposed to do and how it is supposed to work as. This shared ledger version or vision has become the backbone of our distributed ledger technology. So we have already seen what is the shared ledger vision. Now let us see or define the distributed ledger technology. So what is a distributed ledger? So a ledger of any transactions or contracts maintained in decentralized form across different locations and people, and eliminating the need of central authority to keep check against manipulation. This is a definition of distributed ledger. Another definition of distributed ledger is they are systems that enable parties who don't fully trust each other to form and maintain consensus about the existence, status, and evolution of set of shared facts. Now, although it has been mentioned that who don't fully trust each other, the idea when we do transactions is not of trusting, but to make sure that the data or the transactions that we have done is non manipulatable, or someone should not be able to manipulate it. So we now know what is a distributed ledger. Let us have a look at the characteristics of distributed ledger. As you can see, a ledger can be centralized or can be distributed from the figure 1. We further can say that distributed ledgers can be in the form of a blockchain, or they can be in form of a non-blockchain. Cryptocurrency can be taken as an example of a distributed ledger, or ledgers for any banking industry or any other industry can also be considered as a distributed ledger, but they fall under the category of non-blockchain ledgers. Okay. Why they are beneficial? First, they follow cryptographic principles, so we ensure that identity authentication happens for each transaction. They are non-repudiation. They have non-repudiation and immutability, so to preserve integrity of the data, and we can easily do a audit report or audit trail. It follows smart contracts, so we can get automatic execution of certain business logics when the criteria are met. They have a ledger which can be shared, so each participant who on need to know basis will be able to see the data, see things whether they are appropriate or not, and so on. And we get a distributed consensus, so that a state of the ledger and is agreed upon by all stakeholders. Having understood the basic fundamentals, let us now look into Corda's unique shared ledger approach. Corda has been based on or has been inspired by blockchain, and hence it takes the best attributes from cryptocurrencies like Bitcoin, Ethereum, and other aspects. It has been built for financial markets, hence it is enterprise grade. It applies data privacy, as it is not sharing data with everybody on across the nodes. It is all the data privacy is easily implemented. It only propagates the data to the relevant nodes. Instead of having a system level consensus, Corda applies individual deal level consensus and has multiple consensus mechanisms, which will be discussed further or later. Then we have a regulatory focused entity in Corda, because it has been the design directly enables the regulatories to become a supervisor or an observer node. It provides features of smart contract. So there's a direct link between legal prose and smart contract code, which cannot be broken easily. And it also provides easy integration with the existing technologies that are available in the market of programming as well. So few of the Corda's silent features are as mentioned, as you can see in the slide. First and foremost, it is a permission network. It's not a blockchain, hence there is no mining required. Still, it is secured, and a lot of features that we were used to in Bitcoin are available in this particular network. All communications are point to point, and data is not broadcasted to all the nodes in the network, or rather say Corda network. As you can see here, we reject the notion that data should be broadcast to all the participants or to any predefined groups. We have to share the data between only the known entities, and that is the reason why the identity of the recipients becomes very important. As to send a message, the sender needs to know the identity of the recipient. Data is shared on need to know basis and only between the peers, so only they can see and not everybody. Here, if you observe, we have said that not sending is preferable to sending and encrypting. Encryption takes huge amount of time and resource of the computer or the machine that we are using, and as such, encrypting and then broadcasting it takes a huge amount of time in data transaction. Here, as that does not happen, the transactions time is also faster. It also supports unspent transactions output similar to Bitcoin, wherein we can have a check on double spending. It is JVM based, so it's very easy to understand by technical people. They can use Java or Kotlin or any other language to program. It supports industry standard protocols like AMQP, that is Advanced Message Queue protocols. It supports JDBC. It supports public key infrastructure, and so on. It is not a cryptocurrency, but it is capable of representing digital cash. This slide lists some concepts of Corda, which we'll be looking into detail later on. So the first concept is the network, that is the ecosystem that Corda exists in. The second is the ledger, and basically it's how facts on the ledger are shared between the nodes. Then what you have is states. The states represent shared facts on the ledger. Then we have transactions. Transactions generally are used to update the ledger states. Then we have contracts. Contracts govern the way in which states can evolve over a period of time. Then we have flows that generally describes the interaction that must occur between two parties to achieve or to come to a consensus. Basically means to satisfy some business requirement, we need to have a proper flow. Then we have consensus. Consensus basically talks about how two parties agree to a particular shared fact. Then we have notaries, the components that assure uniqueness in terms of consensus, and it generally is used to prevent double spending. We'll be continuing with the concepts in the next slide also. The next concept is vault. It consists of a set of ledgers or a ledger wherein which is stored on a node. Then we have a time window which can be used to validate a transaction. Then we have oracles. These are services that can be used for signing. Then we have nodes wherein each node can contain an instance of Corda, one or more Corda apps. Then we have transaction tear-offs, where transaction tear-offs can be used when we want a party to see only a limited portion of the transaction. Before we go into details of other Corda concepts, let's have a bird view of the Corda network. As you can see here, the Corda network can be segregated into two parts. First is the infrastructure services, and second is the individual node which is going to access the infrastructure services. The infrastructure services communicates with this node using AMQP protocol, Advanced Message Queue protocol, and it provides a secure transition or secure communication between the two entities. The infrastructure services basically consists of notary services, network map, and a permissioning services. We'll be looking into these services in detail. It is also having an association with Oracle node or Oracle services, which also might run a Corda app, and it also interacts with a party, which is basically a person who wants to do a transaction, and the person also requires a Corda node which consists of a set of transactions. So let us now have a look in detail about each of these components. So first one that we are going to look into is the permissioning service. which is also called as a doorman. The job of the doorman is to enforce rules regarding the information that nodes might put or provide before being admitted to the network. We want to make sure basically that any node that connects to a Corda network is an authenticated node. So the node needs to identify itself and show certain aspects to the doorman, and only then the doorman allows that node to be part of the Corda network. So once the domain is satisfied about the node's identity, it issues a certificate which is a root authority signed TLS certificate. The node can become part of the Corda network. Okay, so it also has 2 or more Corda nodes. Why we are saying 2 or more Corda nodes? Because whenever we want to have interaction, we need to have at least 2 entities in that interaction. So we require 2 or more Corda nodes to be part of the accessing mechanism. And basically it runs on JVM, and it has 2 interfaces, one which you call as the network interface, which is used to interact with the other nodes, and second which is an RPC mode, which is used to interact with the node's owner. Then we have a network map service which generally publishes the addresses through which all nodes can be reached, along with the certificates and the services that are provided by that node. Now this also makes us understand that when we say different nodes, the nodes can be classified into different categories. We'll be looking into that a bit later. Okay, one or more notary services also is part of the Corda network. The notary services are used to attest the uniqueness and the possibility of ledger update. So generally what we are trying to do is by using notary services is that we are trying to avoid the double spends. Double spends basically means that a person who has already done a transaction should not use this transaction with someone else. Then we have 0 or more oracle services. They are well known signing transaction entities which can be used to make sure that the fact is considered to be trusted. So moving forward, now let us have a look at the topology of a Corda network. As mentioned previously, a Corda network is an authenticated peer-to-peer network of nodes where each node is a Java virtual machine, a runtime environment that hosts a Corda service and executes an applications that are known as Corda app. Also, the Corda network, as you can see, is a fully connected graph. There are no global broadcasts happening. All communications are point to point, and each of them use AMQP to communicate with each other. The network map service, as mentioned earlier, publishes the lists of peers who can be communicated with, and in the figure the graph edges represent the potential to communicate and does not show that the lines are the connections or persistent connections. As you can see in the figure, we have a node allies. It also has a service which has been mentioned that it provides, that is cash issuer or a bond issuer. We are able to see the address of this particular node along with port ID. So the address here is 192.168.0.3 and the port ID is 10005. And we're able to see the public key of this particular node allies. Now, because we interact based on the public and private key infrastructure, other nodes need to know the public key of this particular node allies. Then we have a notary node, which also at times becomes important, and then we have a permissioning service denoted by 1 or a certificate signing authority which is denoted by 1. Okay, so we have seen what is a Corda network and what are its components. So let us now have a look at a ledger and specifically the peer view of the ledger. As you can see, the definition says that a ledger from peer's point of view is union of intersection with other network peers, and some of which may be empty sets. As you can observe on the screen, you are able to see here 5 nodes: Alice, Bob, Carl, Demi and Ed. Alice has 2 entities in terms of number 1 and number 7. Bob has number 17665, Carl has 946523 and Demi 238, while Ed 948 and 3. Now, what is this 1765 and so on? Basically, they represent the transaction that has been done between the 2 entities. So, for example, The red one that you are able to see indicates that Alice and Bob have done a transaction. Similarly, the number 7 also indicates the same thing, that Alice and Bob has done a transaction. Now, when only Alice and Bob are part of these transactions, no other entities would be having any data sets. So, if Carl had not done any transaction with Bob, Bob would have only 1 and 7. So, Alice and Bob would have 1, 7, similarly 1 and 7. But now, as Carl has done transaction with Bob, we have 6 and 5 in terms of Carl and Bob. The sequencing is not predefined over here. So, as of now, just to simplify, we may assume that there was a transaction 1 which was done by Alice and Bob. Then there was a transaction that was done between Carl and Demi. So, it has been given as number 2. Then there was a transaction which was done between Carl, Ed and Demi, and it has been given transaction number 3. Then there was a transaction between Carl and Ed, it has been given transaction 4, and then Carl and Bob has been given transaction 5, again between Carl and Bob given transaction 6, then a transaction between Alice and Bob, hence it became 7, then between Ed and Demi, hence it became 8, and then between Ed and Carl, hence it became 9. This is for understanding simplicity. It may not be exactly in this particular order. So, as you can see now, everybody, when I'm saying everybody, I'm talking about each and every node, is only able to see the ledgers that or the transactions that they have done with respect to someone else. And this data is not shared amongst all or each of the nodes in the network. Let us take one more view at the ledger in form of a bilateral ledger now. When we say bilateral, we are talking about only two entities here. As you can see, the ledger is not a central ledger. Each network peer has to maintain a fact which is stored in a vault, or you can consider them to be a rows of your database table. Not all on ledger facts have to be shared with other peers. So everything may not be shared with the peers. From the screenshot, you can observe that there is a black square with number 11. Now this black square has not been shared with anybody by Alice, but still Alice has that record or the fact in its vault or in its ledger. Now if you look from the properties of this ledger, we can say it's immutable because it is very easy to do analysis on any of the static data sets that is available to us, and we will get a single snapshot of it as and when required. No accounts, it's easy to apply transactions in parallel, so I don't have to do a transaction in a sequential order, which we mentioned in the previous slide. The ordering of the transaction will never be missed because we are working with hashes. So unless and until we have a hash of the previous state, we will not be able to generate a new state. A consensus is very easy to maintain because if there is a conflict, it basically means there is a double spend problem which can be resolved. And auditability of all these activities is also there because everything is recorded. Now you can observe the two tables below these circles of Alice and Bob contains the transactions. So we have facts, much consensus, so bilateral, and wow ledger. These are general simple demonstrations. You may have any fact within this particular statement. Now observe that Alice has 3 facts while Bob has 4 facts, but there is a two-way array which is visible between Alice and Bob. So we have much consensus mapped with much consensus and so bilateral mapped with so bilateral. The idea behind showing this arrows or two-dimensional arrows is that these two facts are shared between Alice and Bob. Although very fact and amaze are also facts available with Bob, but they are not shared with Alice but someone else. There is a fact called wow ledger which is again not shared with anybody from the perception of Alice. So this is how the bilateral ledgers are stored. So in the previous slide we saw that ledger is a repository of shared facts. Now how do we represent these facts actually? So to represent a fact, what we have in Corda is known as a state. Now state as you can see here represents an on ledger facts and they keep on evolving, and either they are spent or they are unspent. So if they have been spent, they become historical. If they have been unspent, we need to work on them. As you can observe on the screen, a representation of a state has been given to you. There you can see 3 components. One is IAU contract, participants, that is Alice and Bob, and then you have certain properties. Now this particular state becomes an agreement between Alice and Bob. Generally, if you try to decipher this figure, you will be able to understand that this is a contract between Alice and Bob for an amount of £10, wherein it is being represented that the amount should be paid by 1st March 2017, and if you are failing to pay by that time, you will have to pay 20% penalty. Okay. Now, if this particular state is to be taken, we have to assume that they will be stored in a vault, and they will be stored in a vault in such a manner that we will be able to identify what is the status of the transaction as of now. Now, the figure below, as you can see, shows a sequence of states. Now, let us try to understand this particular sequence of states. So, first, when we start, we have a scenario of no agreement. When we say no agreement, there was no agreement between Alice and Bob. And then, on 1st of February 2017, Alice borrows £10 from Bob. Fine. So, once that has been done, what happens is state is created, and that state is Alice owes Bob $10 payable by 2017 3/1, that is 1st of March 2017, and late settlements will be charged 20% daily. This is the information that is provided by that state. Now, assume that after some time, Alice pays Bob £5, and that happens on 24th February 2017. Now, as Alice has already paid Bob the £5, what happens is that we copy the previous state and create a new state out of it, and we mark that state with the sequence statement which is mentioning over here as Alice paid £5, and the date can also be mentioned. Once this particular amount has been transferred, the previous state becomes an historical state, right? So on, we can continue with the states till we are in complete agreement of what has happened, or when Alice has paid Bob and all the state sequence, once even if the agreement has expired, will be stored in the vault. So as and when Alice and Bob want, they can have a look at it and check the authenticity of the records. Okay, so we have looked at states. Now, if you observe that the statements would be that states are the facts that are available on the ledger. Also, we will have two types of states in the ledger. One which is considered to be historic, and one which is unspent. That is basically, we mean to say that we would have to work on them. Okay, so how do we update or how do we convert a state into a historic state? And that is where we have something called transaction. So generally, transactions are proposal to update the ledger. And when you say update the ledger, we cannot directly update the ledger, but we need to check certain aspects, and those aspects are that we have to make sure that there is no double spend on that particular state, the states are contractually valid, and also it is signed by the required parties. Once it is signed by the required parties, only then we will be converting into a transaction, and that transaction will be considered as a committed transaction. Otherwise, it will be a non-committed transaction. Now, transactions generally will consume an input state and will create a new output states. So it is possible that a single transaction may at times contain multiple input states and create a single output states, or vice versa, might contain single input state and create a multiple output states. The newly created output states will replace the input states, and the input states will be marked as historic. So how are transactions created? A proposal for creating a transactions can come from any peer. So in case of our example of Alice and Bob, it is possible that Alice can create a transaction proposal or Bob can create a transaction proposal. Initially, when the transaction proposals come into picture, they are uncommitted by default. As mentioned, they will not be changing the states without a signing. So before a transaction proposal is committed, it must be digitally signed by each and every peer on need to know basis. It is possible that it might be needed to be signed by a third party also, and that third party could be a notary. Also, once the transaction is committed, it marks the input state references as historic, and it creates new output states reflecting that the ledger has been updated, and this updated ledger is then stored in a vault. So in the previous slides, we saw different states and we saw what is a transaction. Now let us have a look at a full transaction. which could be assumed as a committed transaction. Now if you observe the figure, you'll be able to see states IOU1 and IOU2, similarly cache 1 and cache 2, and along with that you are able to see certain other aspects. We'll be discussing these aspects very soon. Now the two states IOU1 and IOU2 are binded with a command called settle command, and they have been signed, or they need to be signed by Alice and Bob. Now, if you remember, we had already mentioned that Alice had borrowed £10 from Bob, and now she wants to settle the amount to a certain extent. So, IOU1 and IOU2 have a settle command wherein Alice is trying to give back £5 to Bob. Then we have next state wherein cache 1, which is cache 1 and cache 2, wherein Alice is actually paying £5 to Bob, and it only needs to be signed by Alice. And then we combine, or we have some attachments. If we want to give that attachments, it could be, the attachments could be anything that we want to share along with this states. And then there's a time window which defines till what this particular states or transaction is to be considered as valid. And because Alice has signed as well as Bob has signed, this transaction can be considered as a committed transaction, which basically means that one party has given £5 and other party has received £5. You have to observe that if it was only signed by Alice, in that case it would have become uncommitted. So both the signs, Alice and Bob's signs, are a must here to commit the transaction. And once the transaction is committed, this entire state would become a historical state. If you observe the current figure, you will get an idea now that vault is something that is stored by every node on which it stores ledgers. Ledgers contain states, generally which are unconsumed and which are historical, and to convert the states to historical activity we require a transaction. So you can observe that at times the unconsumed states B head, A head, C head and S head, in case of this figure, these are the ones which will become part of the next transactions. The previous states have already been marked historic, which basically means that certain transactions have already happened on them and they cannot be carried further. So if you observe, this B head, A head, C head and S head are on the top of the chain, and they are the ones which are as of now unspent or unconsumed, and these are the only states which can go ahead into any transactions. So this represents a vault for a node. Now we saw the concepts of Corda network, a Corda ledger, Corda state, a Corda transaction. Let us have a view of how these transactions actually happen. So what is the flow of these transactions that are supposed to happen? Now if you look at the figure here, you are able to see that there is an initiator called Alice. So he will get some data from an external system or an internal system. He will create a transaction called TX, then he will sign the transaction TX, and the flow of Alice stops at this particular point as of now. Then this IOU, or rather say state that has been created, will be sent to responder Bob, who will inspect and verify whether the transaction is correct or not, again sign that transaction, commit that transaction and send the signature and the transaction to Alice to verify. And once it has been again verified by Alice, it will be committed, and that is where we'll be getting the full transaction that we saw in the previous slide. The figure below in terms of topology shows the red dots, which says that Alice and Bob do the activity. Although animation is not available over here, we can assume that Alice is sending the communication to Bob, Bob is sending communication back to Alice, and in case there is a requirement of a notary, Alice might send it to notary, and then notary might send it back to Alice, and once that happens, the transaction will become a full transaction and a committed transaction, and all the previous or states that were there will become historic. In the previous slide, we mentioned that we need to verify the transaction, or the parties do verify the transactions. Now, the verification basically is a consensus process wherein the peers reach to consensus over the transactions, and in Corda it is done in two ways. So what we have is two types of consensus. One is verification consensus and second is uniqueness consensus. The verification consensus basically involves the two nodes that are doing the transaction. Both the peers require to sign the listed commands of a flow, whichever has been mentioned. So in the previous slide, if you observe, there were two commands. One is settle and another was pay. So both this have to be signed. If things are okay, that sign will be considered as fine. And then I mentioned in the previous slide again that if mandatory, we may send it to the notary. So the notary is supposed to check for the uniqueness of the state. Basically it means that whichever states that have been used in the transactions, they have not been used more than once. We are trying to check here the double spend. What do you mean by this particular scenario over here? Now try to assume that when Alice is returning back £5, what if the state that was having this £5 has been used by Alice in two cases? So for example, Alice gives the same state to Bob as well as to some third party, Kathy. In that case, someone needs to verify that this is not the same state that has been given to both the parties, and this is where the notary comes into picture. So once the notary verifies that fine, there is no such entry available in his database, then this particular uniqueness consensus becomes valid. So that's all folks from my side. We have seen some basic concepts of Corda, and if you want to get more resources or more information about Corda, please visit www.corda.net. If you want to go into technical aspects of implementing Corda, please go to docs.corda.net/docs cordaos/4.4 quickstart-index.html. You will be able to see implementation scenarios, the prerequisites of this particular Corda, and all other aspects that you would be looking for in terms of developing a Corda app. So thank you very much. Hope you enjoyed the presentation. Please give me your feedback at harshal.arolkar@glsuniversity.ac.in.